everyone, this is Dr. Sandeep, Associate Professor in the Department of Mechanical Engineering, working in Institute of Aeronautical Engineering, Hyderabad. Today's topic is unit cell, space lattice, crystal structure and its types. So we are going to discuss about unit cell, space lattice, crystal structure and its types. So crystal structure. So what is the use of crystal structure? So any solid material, it can be classified according to the type of crystal structure. So depending upon the type of crystal structure, the solid material is being classified. So how this crystal structure, the arrangement of the structure, whether it is a regular or irregular arrangement. So depending upon the regularity of the arrangement, whether it is a irregular or regular arrangement, you can easily describe the material characteristic. The solid material can be classified based upon the classification of how the crystal structure is there in the material. Now, what is a crystalline material? We are talking about crystalline structure. So before going to the crystalline structure, what is a crystalline material? So this crystalline material is one in which the atoms are situated in a repeating periodic array. Okay. So repeating periodic array is nothing but, so here you can see you have an array like this, and this array is being repeated over a large atomic distance. So this is being repeated like this. It is being repeated in all the directions, in all the XYZ directions, internally, externally. So, any material, a crystalline material in which the atoms are situated in repeating of the periodic array over a large distances. So, this type of arrangement is called as a crystalline material. So, in this example, you can see in all the three directions, the 3D model, so it is being arranged in a repeating or periodic array over a large distances. So this type of thing is called as a crystalline material. And the long range order exists. How it is exists? Such that depending upon the solidification. So if there is a huge gap, the time taken for solidification is very high. If it is very less gap between the atoms, the solidification time is very less. So in such a way that you have to describe any given solid material. So now this position, the atoms, what are the atoms you have in this? So these are all the atoms. The position of all the atoms are again repeating themselves. You can see all these three, green, red, all these things are being repeating each other themselves in a three-dimensional pattern. Now see this figure, you can observe whatever the atoms are there. So these atoms are being repetitive in 3D nature, repetitive in 3D pattern, in which the atoms are bonding nearest to the neighbor atoms. So here the atom is bonding to this which is nearer. Here this is near, again it is bonding. Where here it is nearer, it is again bonding. Here it is near bonding. So in such a way that the atoms which are near or neighbor to each other, and there should be a bonding between them. And also the atoms are being repetitive in nature in a 3D pattern, and the crystalline material are to be situated in a repeating periodic array. So all this category describes a crystal structure. So here we have, first, what is the thing you need to have? The atoms should be situated in repeating periodic array. So repeating periodic array. So this is the repeating periodic array. This is one category. And what is the other category? There should be a order. There should be a order, and each atom should position themselves in repetitive. Each atom should be repeating themselves with each other, and these atoms to the neighbor atoms, there should be a bonding between them, like this bonding. Wherever you find the neighbor, they should have a bonding. So all these things comes under the crystalline structure. So where you can find this crystal structure means all metals, many ceramics, materials, and certain polymers from crystalline structure under normal solidification conditions. And some of the properties of the crystalline solids depends upon the type of crystal structure. So some materials, they should take time. They will take a lot of time to get solidification, and some material will take very less time to get solidification. Why? What is the difference? Because of the crystal structure. Since the atoms are away from each other, the distance between the atoms is very high. Okay, so during the solidification time, it takes less time, very high time to get closer to each other to get solidification. So that's why the properties, some of the properties like solidification time or strengthen of the material or the ductility nature or the tensile nature, all these types of different physical natures can be differentiated depending upon the crystal structure. So there is an extremely large number of different crystal structures we have. We have a lot of different crystal structures which having a long range of atomic order, and these vary relatively from simple structure to for metals and complex ones also. So since you have n number of materials and each material will have its own atomic structure starting from simple to complex in nature. So if you know all these atomic structures, the crystal structures, you can easily know the nature of the material. If you know, once you know the nature of the material, then you can easily justify the material for the required application. So now when describing any crystal structure of atoms which is having ions or of being solid sphere, which, okay, by taking a solid sphere with a defined configuration, well defined diameters, you can easily describe what type of crystal nature it is, and this termed as atomic hard sphere model. So this is an example of an atomic hard sphere model you can see here. That means when it is said to be hard in nature means the bonding between the nearest neighboring is very strong. Okay, what are the bonding existing between the neighboring atoms is very strong, then that substance, that material is said to be hardest material. So this is an example of hard sphere model for the atomic arrangement. So you can see the neighboring atoms are being bonding between them in all the directions. This is only front view. Back view also you have bonding if you see the back side. So in all the directions, if the neighboring elements are being strongly bound to each other, and this is said to be a hard model, hard sphere model. And in this particular case, all the atoms are identical. Yes, all the atoms are identical, and sometimes the term lattice, okay, sometimes term lattice is used to context the crystal structure. What type of lattice you have? A crystal lattice like that, you have different types of lattice structures. So these can also be termed in terms of lattice. Whatever the crystal structure is there, this can be termed in terms of lattice. And in the sense, nothing but lattice is nothing but it is in the 3D, three-dimensional view, where the points are coinciding with the atom positions. Now, here you can see the figure A. You have here a face centered. Why it is called a face centered means this is the face. It is exactly at the center, and all the atoms are being bonding here. So this is called a face example, face centered, and this is a solid hard sphere. Now this hard solid sphere is reduced to a unit cell. A unit means a one single unit. So now this, in order to find out the properties, we can't find at one stretch. That's why you have to take a unit from that solid hard sphere, and this unit you have to calculate, and then you can integrate to get the whole strength or some properties of the material. Now what we are doing here, we are considering a hard sphere, the figure A. From this figure A, we are trying to reduce into a unit cell. Now the figure B is called as a unit cell. Okay, so one unit we are taking One unit we are taking from that lattice, from that atomic structure. And how we are taking means, so you can see the figure C. So this is the aggregate of many atoms. So you have n number of atoms in this aggregate. All adding of all the atoms, we are getting this aggregate of many atoms. From this we are taking a unit cell. So this is called a unit cell. What are the unit cell we have? This we are taking here like this. In order to find what is the type of structure, whether it is a face centered or body centered or hexagonal structure, based upon this unit cell, we'll decide. So depending upon that structure, we'll know the characteristics of the material. So this is how you have to consider a hard sphere model. From that hard sphere model, you have to take a unit cell. So for this unit cell, you have to calculate all the property values. Now what is unit cell we are talking? We are considering a small one unit like this from a bulk aggregate model. From a bulk aggregate model, we are taking a small unit. So this is called as a unit cell. And here you have all the atoms which are again bonding to each other. All the neighboring atoms are being bonded to each other. So the atomic order in crystalline solids indicate that smallest group of atoms form a repetitive nature. So what is the smallest group here? So in this total aggregate model, you have, this is the smallest model. So if this smallest model is arranged in a repetitive model, then you can form an atomic structure, crystal structure. So this is being repeating in nature. Once this is being in repeating nature, you can get like this, all the, like this. Okay. So again, we'll get all the bonds. So smallest group, when you consider from all the aggregate, that is called as a unit cell. And this unit cell, if it is repeating in nature, then you can get the structure, atomic structure. And this structure may be face centered or body centered or hexagonal centered. So that we need to study depending upon the nature of the bonding between the atoms. So this is called as a unit cell. And this unit cell is chosen to represent the symmetry of the crystal nature. Why we are considering this unit cell means, if you want to know whether it is a symmetry or unsymmetry, if you take one unit cell, if you repeat this unit cell in a repeating order to form an array of group of array, so this unit cell represents whether it is symmetry or not. If it is not symmetry, then it comes under another category. If it is symmetry, it comes under symmetry category. So like that, the unit cell helps us to find out whether it is a symmetry or unsymmetry in nature. So within all the positions, atom positions in crystal, it may be generated by translation of the unit cell into integral distances along each edge sides. So what is happening? We are considering one unit cell from the aggregate and we are trying to calculate the values of that one unit cell. Then if you integrate all the unit cells, then you can get the complete value of that body. So once at a time, we can't completely find out the values of a particular solid body. From that solid body, we have to take some element, some small element. You have to calculate the values of that small element. Then if you integrate that element with the upper and boundary layer limits, then you can easily find out the complete value of that solid elements. So that is the useful of the unit cell. First one is what? We can get the symmetry nature and we can find out the total, we can get the total value of the solid body. So these are the usefuls of unit cell. So that's why the unit cell is the basic structure of the unit. So depending upon that basic structure only, you're trying to get the complete structure of the element what we are trying to consider. So this is conveniently used to dictate the corner sides which are being coincides. So once you know the unit cell, like this, we can easily find out what are the corners whether it is being bonding in nature or not? Is it not? If you know the unit cell structure, then we can easily find out what are the corners which are being coinciding and where we are getting hard sphere atoms. Hardness means where there is a strong bond. So if you know the bonding between the unit cell, then it is very easy for us to find out whether it is a which type of material, whether it is a hard material, and where the corners are being coinciding to each other. If you know this, then we can do the repetitive nature and we can find out the whole structure of the atom. And coming to the other thing, the space lattice. It is a space lattice. So a space lattice, again, it is an array of points showing how particles, that is nothing but the atoms or ions or molecules, are arranged at different sites in a 3-dimension. So this is a 3-dimensional view in a space. So here, again, array of points. So array of point showing how these atoms, molecules or ions are being arranged at different sites. So you have here atoms, whether they are arranged in a cubical way, hexagonally, spherically, you can find out by this space lattice. That's why this space lattice is nothing but it is an array of points. It is an array of points showing the molecules, ions or atoms, how they are being arranged at different sites in a 3-dimension. So depending upon this space lattice, you can easily find out the nature of the material. Now the other thing is what? Metallic crystal structure. So what is the metallic crystal structure? Means the atomic bonding in this group of materials is metallic and thus non-directional in nature. It is a non-directional in nature. Only the atomic bonding in this group related to only metals. Okay, wherever the metals which are being bonding to each other and non-directional in nature. Okay, that type of thing is called as a metallic crystal structure. And 3 relative simple crystal structures are being found in this category. So first one is the face center cubic structure. This is the face center. Second category is body centered. And third one is hexagonal close packed. So how we are differentiating based upon the unit cell again. We are talking about unit cell in the previous slides. So unit cell, it will give the information about the how is the bonding between the adjacent atoms, neighboring atoms. Depending upon the bonding between the neighboring atoms, we can find out whether it is a face centered, body centered or hexagonally closely packed. Now if you see the first category, so depending upon this, you can't tell. This is a huge aggregate solid sphere. So like this you can't tell. But if you take a unit cell from this, this is the unit cell what we are taking. Now, this is exactly at the face center. Okay. Now, if you see the bonding, so to this face you have at center, and for this face you have center, and for the bottom also you have the center, and this side also you have center, and this side also you have center. Everywhere, at every face of that cube, you have a center bonding. Okay, at every face, whether top, bottom, right, left, front, back, all the faces, exactly at the center you have a atom which is being bonding to the other neighboring atoms. So based upon this, you can tell that it is a face-centered cubic structure. All the faces you have at the center. So from the center, it is being bonding to the neighbor atoms. That's why it is called as a face-centered cubic structure. So that is the first one. The second category is body-centered. To the whole body exactly at the center. So this is a cube. For the whole cube, exactly at the center, you have an atom. And this atom is bonding to all the neighboring atoms like this. So that's why it is called as a body-centered. Next comes the third category in the metallic crystals. We have the hexagonal. Why it is hexagon? Again, we have here 1, 2, 3, 4, 5, 6. Again, the base 1, 2, 3, 4, 5, 6. So, for this hexagonal, you have at the center, top and bottom, and these are being bonding with all the corners. of the top and bottom, and again at the center you have hexagonal. So that's why it's hexagonally closely packed. So like this, you're differentiating the type of crystal structure depending upon the unit cell. On the whole, you can't tell whether it is a face center, body center, or hexagonal center. From the aggregate model, from the solids model, you have to take some small part of unit cell. From that small part of unit cell, you have to know how the atoms are being contacted, how the atoms are being bonding to each other. Depending upon that, you can differentiate all these three categories. Now, one by one, we'll see what is face-centered, body-centered, and hexagonally closely packed. First one is the face-centered cubic structure. The structure found for many metals, the structure, crystal structure found for many metals have a unit cell of cubic geometry. So most of the things, most of the metals are having a cubic unit cell geometry with atoms located at each corner and the center of all the cube faces. So in this category, what is happening? Most of the metals are having cubic in nature. So for this cube, at all the corners you have the atoms, and these atoms are being bonding at the center of all the faces. So that's why it is called as a face-centered cubic structure. And it is aptly the face-centered cubic FCC crystal structure, and some of the familiar metals which are having this type of FCC crystal structure are copper, aluminium, silver, and gold. Okay, so the cubic nature, in that cubic nature, if all the faces of that atoms are being contacted with all the corners, that is called as a FCC. Okay, and this FCC are having copper, gold, aluminum, and silver are the best examples which are having this FCC type of crystal structure. So this is the face-centered cubic structure we can see. So this is a figure A is a hard model. What I told, by seeing this hard model, we can't tell that whether it is a face-centered or body-centered. Now, since we know this small element, so this is the 3D model unit cell. From this, we are trying to come with this model of unit cell. So what is happening, you can see clearly, this is the face of this body, and this is exactly at the center. That's why it is face centered, and this atom is again bonding to all the corners. You can see here, this is at the exact at the center. Now this is being bonding to all the corners. Only this is the first face, front side we have to see. If you see the back side also, you can see this is the back side, this is another side, left side and right side. This side you can see this side. So all the four sides, even the top, bottom. So exactly the center of the face of the cube, if the atom is being bonded to the corners of all the elements, that type of category is called as a face centered. And this you can describe by taking a unit cell from the complete body. And the aggregate of atoms. So this is the aggregate, what I told. So this is the complete aggregate of the atom. And from this aggregate, you're trying to take a small unit. This is a small unit. If you take that small unit, and if you identify how the bonding is there between the atoms, which corners, whether it is a face centered or body centered, you have to observe. And from that, you can define whether it is a FCC or BCC or HCP. Now in this category, since it is exactly at the center of all the faces, that's why it's called as a FCC unit cell. And if you want to find out the atomic radius, of the FCC, then you have the formula of A equal to 2 into root 2, 2r into root 2. So what is here? A is called the length of the cube edge. So this is my cube. cube. So this is the edge length A. If you want to find out this atomic radius, this R, if you want to find out the atomic radius R, then you have the relation between the atomic radius and the edge length as A is equal to 2 into R root 2. So this is the formula you have. Then you can easily find out what is the atomic radius related to the edge length of the atom. So A equal to 2R root 2. By using this formula, you can easily find out what is the atomic radius. So this is about the face-centered. You have different formulas for different face structured cubic structures. Now, for the FCC crystal structure, each corner, what is happening here? Each corner atom is shared among 8 unit cells, is it not? Each corner is sharing about 8. So, whereas face-centered belongs to only 2. Face-centered is belong to only 2. Therefore, total how many you have? 1/8 of each of the 8 corners atoms and 1/2 of the each of the 6 atoms. So, total you have 4 atoms. 4 atoms are there. So, this is for FCC. And this figure depicts about the FCC where only sphere portion is represented. How we are getting 8 means, see here, 1, 2, 3, 4. Similarly, on the back side also you have 1, 2, 3, 4. So, total you have 8 combinations here. So, all the 8 you have here. So, by taking all those 4 and 4, you will get 8. Now, 2 other important characteristics of the crystal structure are the coordination number and the atomic packing factor. And these are very, very important. So, depending upon the atomic packing factor as well as coordination number, you can tell the bonding nature between the elements. Now, for us, for metals, what is happening here? Each atom has the same number of nearest neighboring or touching atoms, is it not? So, since it is being contacted like this, so all the atoms are being like this. So, if you find out the coordination number, you will get 12. All the sides, 4, front, back, left and right, 4 plus 4 plus 4, total you will get 12. So, total coordination number for FCC is 12. And if you want to find out the atomic packing factor, so what is the formula for atomic packing factor? Here is atomic packing factor is the ratio between the volume of atoms in a unit cell to the total unit cell volume. Atomic packing factor is the ratio of volume of atoms in a unit cell. So, what are the volume of that atom in a unit cell? So, we are calculating only for unit cell only, not for the whole entire body. For unit cell, we are trying to calculate what is the volume of atoms, how many atoms are there in a unit cell to the total unit cell volume. So, that is gives us the atomic packing factor. So, in case of FCC, the atomic packing factor is about 0.74. So, this is the maximum value. This is the maximum possible packing factor value for spheres which are having the same diameter. Now, what is the importance of this atomic packing factor? If you have a high atomic packing factor, that means there is a strong bonding between the elements. So, if you have a less packing factor value, atomic packing factor value, then there is a bonding, there is a less amount of bonding between the elements. So, you have to select a material which is having higher atomic packing factor value. If you have a higher atomic packing factor value, then that metal is very, very suitable for a good hardening material. So, this is one of the factors when selecting any material. APF, atomic packing factor, should be considered. So, this is 0.74 for FCC. So, for different atomic structures, you have different atomic packing factor values. For FCC, you have 0.74. This is the maximum value for all possible spheres which are having the same diameter. Next comes the body centered. Body centered again. How we are defining this body centered? So, depending upon, again, you have to take a unit cell from the aggregate. From that unit cell, how the atoms are being bonded to the corners of the element. Exactly at the center of the body, you have to take that center atom is being bonded to the corners of the other element. So, depending upon the type of category, you can tell that it is a body centered. So, Another common metallic crystal structure has a cubic unit cell, in which what is happening, atoms at all eight corners, and a single atom at the cubic center. Okay, at this center, so this is the, so at this center you have a single atom. So this atom is being bonded to all the corners. So this is called as a body centered. Exactly, the body, at the center of the body you have an atom. This is being bonded to all the corners. Then that type of crystal structure is called as a BCC, body centered cubic crystal structure. The face is also a cubic in nature. So now if you want to find out the atomic radius related to the body centered, then you have the formula as A is equal to 4r by root 3. So in the FCC you have another formula, that is A equal to 2 into root 2r. So that is, see, depending upon the type of crystal structure, you have different formulas to find out what is the atomic radius when compared to the length of the cube. Okay, so in this case you have A is equal to 4r by root 3. So if you know this relation, you can easily find out what is the radius of that edge length. Now this is the how you can find out from this. This is the aggregate of the body center, and from this body center you have to take a unit cell. This is a small unit cell, and we are coming like this. Now how you are telling that this is a body center? So exactly to the body you have a center atom here, and this center atom is being bonded to all the four corners like this. So that is how you can differentiate the characteristics of the material. So this is a body centered crystal structure. And what are the examples, or what are the materials which are having body center are? Chromium is one of the element, iron, tungsten. These are all the different elements which are having the BCC structure in nature. And two atoms which are associated with each BCC unit cell are nothing but the equivalent of atoms which forms the 8 corners. So in this case also we have 8 corners. Each element is being shared with among the 8 atoms in the unit cell. And finally we have the atomic packing factor is 0.68. We are having very less atomic packing factor when you compare with the FCC. FCC is having 0.74, that is the highest value, but the atoms which are having BCC phase, they will have less atomic packing factor value. That's why again, selection of material, one of the criteria is APF, atomic packing factor value. So the elements which are having lesser values of atomic packing factor should not taken into consideration. Though it is having good properties, other properties, but one of the criteria is APF value. So in this case, we are getting very less value, lower value of 0.68. So wherever the bodies wherever the materials which are having BCC structure in nature will have 0.68. So when you compare with the 0.74 of FCC, so FCC is having a higher rate. So this is about the body center, and the final category is about the hexagonal closely packed crystal structure. So where you can find the hexagonal closely packed crystal structure means not all metals have a unit cell. See, every material will don't have all symmetry in nature. Different materials will have different structure. So most of the metals may have cubic structure in nature, but some metals won't have the cubic nature. So some will have another shape. Some metals will have different shapes. So those materials comes in under another category, comes in hexagonal closely packed. That's why not all metals have unit cell with cubic symmetry. In the previous FCC or BCC, we have seen cubic in nature. So it is very easy for us to find out how the atoms are there, how many atoms are being bonding with the corners or to the faces, and we can easily find out the atomic packing factor number, and also what is the coordination number also we can easily find out if it is a cubic in nature. Now some metals which are not cubic in nature comes under this hexagonal closely packed crystal structure. So the final common metallic structure discussed in this is about the hexagonal nature. So now you can see this figure, you can easily find out by seeing that it is a hexagonal shape. So again, this is a closely packed aggregate model. From this we are taking a hexagon. You can see here. In the previous cases we have taken cubic nature. But since it is in hexagon nature, we have to take a hexagon unit cell. So this hexagon we are taking unit cell like this. In the previous cases for FCC, BCC we are taking cubic in nature. But since all the atoms are not in symmetry of cubic, we are taking this hexagon nature. Now we are converting this aggregate closely packed into a unit cell of hexagon. Now you can see at the base you have 6 and each are being bonding with each other. And again at the top also you have 6, 3, 4, 5, 6 and again all are being bonded to each other. Now if you observe closely, this center of top and bottom, these centers are being bonded like this. Okay, the top and bottom faces, the atom which is exactly at the center of the hexagon, the top and bottom are being bonded like this. And again at the center of this corner you have another atom, at this face you have another, at this face you have another, and these are again bonded with each other. So every atom, wherever it is there, it should be bonded to the neighboring. Then only you'll get a strong bond between the elements or the atoms. Okay. So here also we are trying to take a small unit cell from the aggregate closely packed, which is in a hexagonal shape. In the previous we had taken cubic in nature. So now the top and bottom faces of the unit cell consists of 6. Is it not? At the top and bottom we have 6 atoms, and that are from regular hexagon. Of course, another plane which provides 3 dimensions. That means exactly at the center we have another plane. So this figure shows. So here we have 6. So at the top you have 6, bottom you have 6, another plane 3. 6, 3 and 6. Is it not? The same thing we are trying to explain here in this slide. The top and bottom of the face unit cell having 6. And at the another plane, at the exact, we have 3 additional atoms are there which are being bonded together. And this is again connected to the top and bottom planes. Now these atoms in this mid plane have the nearest neighboring atoms on both the adjacent of the 2 planes. Is it not? Now what is happening here? The equivalent of 6 atoms which are contained in unit cell, that is what are the 6 atoms are there which is contained in that whole unit cell, 1/6 of the atoms, that means 12 top and bottom faces of the corner have 1 each of the 2 center face atoms. So total how many we can have here? 3 in the midplane interior atoms. Therefore, the ratio will be in the range of 1.633. And coming to the atomic packing factor, here we have it is almost equal to 0.74. This is exactly equal to the FCC. So FCC and HCP are having both 0.74, but when you compare the BCC, it is having 0.674 like that. So this is having very less value. Now these two atomic packing factor, so the materials which are having FCC, HCP are having a good bonding nature when you compare with the BCC. So depending upon that atomic packing factor value, you can easily select the materials which are having this FCC or HCP nature rather than BCC. Okay, that's why the importance in the earlier starting slides we have discussed that what is the importance of studying the atomic nature, crystal structure. To define any material, to characterize any material, one need to study the crystal structures. So if you know the crystal structure, then you can easily find out what is the FCC, what is the atomic packing factor, what is the coordination number. So if you know all these things, again selection of material is very easy for us to know. Now if you see this atomic radius and structures for all the 16 metals. So you have aluminum. So if you want to select any metal, any application related to aluminum, then it is having an FCC structure. How we can know? If you know the atomic structure, then it is FCC. What is the atomic radius value? It is 0.143. So like that, different materials will have different crystal structures, though it is having same crystal structure. So in this case, you can see here, copper is having FCC, and gold is also having FCC, lead is also having FCC. Don't think that these three, copper, gold, aluminum, will have the same values of atomic packing factor as well as atomic radius. No, though they're having the same phase, but see, you can see here, the atomic radius is varying. It is 0.128 Newton meter, nanometer, and for gold it is 0.1442, and for lead it is 0.750. So that's what it varies. That's why selection of material will be very, very easy for us if you know all these crystal structures, and if you know all the atomic packing factor values, if you know what is the coordination number, then selection of material will be very, very easy. So that's why you need to study all these things before selection of any material to any given application. So here also you have some molybdenum, it is having BCC, tantalum is having also BCC, tungsten is also having BCC. So here we have taken some 16 different metals which are having different crystal structures with different atomic radius values. Yeah. So now the conclusion is nothing but, if you know all these structures of any type of atoms, element, molecule, or any type of element, it is very, very easy for us to find out the best material selection to the given application. Okay. With this, we can conclude this session of crystal structure. Now, these are some of the references where you can find the information about the crystal structure. First one is about the Introduction to Physical Metallurgy by Sidney Heavener. This is a McGraw-Hill edition. And the second referential book is Essential of Material Science, Donald. This is also Thomson Press edition. Next, Materials Science and Metallurgy. This is one of the book where you can find about the structures, different structures. The author is Kodigiri. And the last one is Material Science and Engineering by William Castler. So from these books, you can get the information about the types of structures, how to take the unit cell, how to calculate the atomic packing factor, how to find out the coordination number. So depending upon these, how to select a material for your application. So these are all some of the references where you can get the information related. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.